this video lesson, we're going to cover the basics behind energy and how energy relates to heat transfer, specifically with a concept called specific heat. Before we can talk about specific heat and the formula, we first need to go through energy and what energy is. In the simplest definition, energy is the ability to do work. Think of it like this way. Energy could be thought of as like money. If you have money, you have the ability to buy a shirt, buy a car, buy a house, buy lots of things. You can donate money, you can transfer money, you can do lots of things. In the same way, if you have energy, you can do a lot of things as well. You can move an object, make it spin, make it go up and down, and so on. Now there's different types of energy, and we're going to cover just a few. The first type of energy is a review of what we've already learned. Kinetic energy. Remember, with kinetic energy, it has anything to do with an object in motion. If an object is moving, it has kinetic energy. Another type of energy is what's known as potential energy. Potential energy is based off of position. Now, position could be in the vertical sense or in the horizontal sense. For instance, suppose you have above the ground a ball of a certain distance. Because the ball has a potential to fall, we would say that it has potential energy. This is energy in the vertical sense. You also have potential energy in the horizontal sense. Take, for instance, a spring. Now let's say you took that spring and compressed it even closer. Because the spring is compressed, it has the potential to move outward, or in the horizontal sense. It also has potential energy. The third type of energy we're going to talk about is what's known as chemical potential energy. Now, chemical potential energy is very similar to potential energy in that it has the potential to do work. However, it's not based on position, but instead is based on composition. In other words, what it's made up of. Take, for instance, a 9-volt battery. A 9-volt battery has chemicals inside. The chemicals inside, or what it's composed of, is what gives it its energy. Its energy to power something or deliver an electrical current. We would say it has chemical potential energy. There's many more types of energy, such as nuclear energy, mechanical energy, and thermal energy, but these are the ones that we're going to focus on right now and see how they relate. Let's do a little practice. Pause the video, and during this pause, I'd like you to go through these 5 examples. In each example, I'd like you to determine what type of energy would be involved in each example. Please note that some examples could be more than one type of energy. So pause now and do these 5 on your own. All right, the first one, car battery, is chemical potential energy. The second one, roller coaster at the top of a hill, could be viewed in one of 2 ways. Since it's at the top of the hill, it has the ability to go down due to gravity, and therefore it does have potential energy. However, if it's moving at the top of that hill, it is also said to have kinetic energy. Number 3, a compressed spring. Since it's compressed based on its position, it does have the ability or potential to decompress in the horizontal sense, and therefore it is potential energy. Notice it's not kinetic because the compressed spring is not moving. Number 4, sitting on a ski lift. A ski lift is raised in the air, and therefore you have the ability to fall. Therefore, you'd have potential energy. If the ski lift is moving, it also is having kinetic energy as well. Finally, a bowling ball rolling down the lane is purely kinetic. Now we're going to look at energy in a different sense. We know what energy is. We've talked about a few examples. Now let's go back to that money example. Let's say you have $500 in your checking account, and you'd like to transfer it to your savings account. Do you lose that money? No, you don't lose the money. You could say your checking account has lost the money, but the money itself has not been lost. We only say it's been transferred. In the same way, energy cannot be created or destroyed, but instead is transferred as well. If you give your friend $10, yes, you may have lost $10, but it was gained by your friend. The $10 still exists. This is the essence of the law of conservation of energy. Now that we know energy and the law of conservation of energy, let's talk specifically about how this will relate to thermochemistry. Anytime energy is transferred from one thing to another, heat is often present. You might have known this, for instance, if you transfer energy from one hand to another by rubbing them together. This generates heat. Now, what is heat? First of all, it is extremely important to note that heat is not the same thing as temperature. Temperature, remember, is just an average measure of the kinetic energy of the molecules. In other words, how fast they're moving. But what makes a molecule move fast or move slow? It's the heat. So you see that heat and temperature depend on one another, but they are not the same thing. More specifically, heat can be defined as the process of energy flowing from a warmer object to a cooler object. There are two ways heat can be represented, Q or H. At the beginning of this unit, we're going to talk about heat in reference to Q, but later on we'll see how it is a reference to H. But it is important to know that they're both the same thing. Now, a few units ago, we did learn about endothermic and exothermic. Let's remind ourselves what they are and then correlate it to what we've just learned about flowing heat energy from one thing to another. Remember, endothermic is where heat enters a system. Take a look at the picture below. You have an Erlenmeyer flask with certain contents in there. Note that it says the contents are cooler than the surroundings. Well, according to energy heat flow, heat will always flow from a warmer object to the cooler object. In this case, the surrounding is warmer than the actual contents in the flask, and therefore heat will transfer in. On the other hand, exothermic was a process where heat exits. In this case, the Erlenmeyer flask is hotter than the surroundings. The surroundings are cooler, and therefore heat flows from the flask outward, exiting the area. Now, the contents that is in both flasks, whether here or here, how do you refer to them? What do we call the contents in which heat is either entering or gaining? We call that the system. The system is the particular container, reaction, area, etc. that we're concerned with. When we're in a lab mixing chemicals in a beaker, it's the beaker and the chemicals inside that we're concerned with. We're not concerned with, let's say, our friend at the next table, the book that's in the cabinet, or the teacher that's sitting at the desk. Those would be what's known as the surroundings. Notice the surroundings is everything other than the system. So in comparison, the system is very small compared to the surroundings. It's important to note that when you are determining whether or not something is endothermic or exothermic, it's always in relation to the system. Therefore, identifying what the system is crucial before you identify if it's endo or exo. Let's do some practice with that now. On the screen in front of you, you see 6 examples. What I'd like you to do in each example is I'd like you to first identify what the system is. This is up to you. Once you do that, then determine what is exo or endo. I'm going to do the first example for you, and then you will do 2 through 6. All right, number 1, your hand touches a cold cup. Some of you might be thinking, oh, I think the cold cup is the system. That's the part we're interested in. Others of you might say, no, it's not the cold cup. It's your hand that we're interested in. Which one is right? The answer is yes. They're both correct. The system is whichever one you're concerned with. Once you've identified what the system is, however, that will help you in identifying whether it's endo or exo. So let's start with the cold cup. Let's say you thought the cold cup was the system. All right. Is heat leaving your hand and going into the cold cup? Or is heat leaving the cold cup and going into your hand? The answer is heat is leaving your hand and going to the cold cup. That's why it feels cold, because heat is leaving your hand. So in reference to the cup, it's gaining heat or absorbing heat, and therefore that's known as endothermic. However, what if you said the system was not the cold cup, but your hand? All right, remember we decided that heat is leaving your hand, and therefore since it's leaving your hand, that would be an exothermic reaction. So I want you to notice that it could be endo or exo depending on what the system is. For every endothermic reaction, there must be an exothermic reaction. Go ahead and pause the video now and then do the remaining 5. Then I will reveal the answers. All right, let's look at number 2. If you said the jacuzzi was the system, the jacuzzi is losing heat to your body, and therefore it's exothermic. However, if you said you are the system, so getting into, then you are gaining heat, and therefore it's endo. Number 3 says you played ice cream on a kitchen counter. Suppose you say that the ice cream is the system. Well, what makes the ice cream melt is that it's absorbing heat, and therefore it would be endothermic. However, if you said the kitchen or the counter was the system, it would be losing heat, and therefore it would be exo. Number 4, walking into a walk-in freezer. If you say the freezer is the system, then the freezer is gaining heat, and therefore it's endothermic. However, if you are the system, then you are losing heat. That's why you feel cold, and therefore it's exothermic. Number 5, walking into a building during December. Buildings are usually kept at a constant temperature, whether it's 75 degrees Fahrenheit or whatever the deciding building decides is the temperature. However, if you are outside in December, you'll usually feel that it's cold. If you walk into the building, you're going to feel warmer. That's because you're absorbing heat from the building. And therefore, if you are the system, you would be experiencing an endothermic reaction. However, if you were to walk into a building, once again at 75 degrees Fahrenheit in August, you would feel that it's much cooler because outside it's very hot. You are losing heat, that's why you feel cooler, and therefore you'd be experiencing an exothermic reaction. These two graphs right here are visual representations of what kind of reaction is happening. Take a moment and decide whether it's endothermic or exothermic. By taking a look at graph number 1, I see that the reactant's energy is higher than the product's energy at the very end, which tells me that heat must have been lost going from the beginning to the end. If heat was lost, then therefore it must have been exothermic. On the other hand, in this graph on number 2, the energy of the reactants is lower than the energy of the products. Heat or energy must have been gained, and therefore it's endothermic. Now that we've talked about energy and what it is, we're now going to transition to quantifying energy. In other words, measuring it. Before we can do that, we need to decide what are the units of measurement we'll use. There's 2, the calorie, represented by CAL, and the joule, represented by a capital J. From here on out, we're going to use more oftentimes than not the joule. This is the SI unit of measurement for energy. Now notice below, you might have remembered that calories is what we see in food. If you look at the back of your nutrition facts, you'll see that your food might possibly be 200 calories. Notice though on the back of your food that it's calories with a capital C. Well, what difference does that make, you might ask? Well, it's not just grammar, it's also representing measurement. 1 big C calorie is equal to 1,000 little c calories. So if you look at the back of your food and it tells you that it's 200 calories, really what that means is that it's 200 or 2 million calories. Quite a big difference. Now let's say you have to convert from joules to calories or calories to joules. The following conversions are what is used. It's important to know that both of these conversions are the same. In other words, they'll give you the same answer. It's just what they're being in reference to. By that I mean this. The first conversion represented equal to 1 calorie, whereas the second one makes it equal to 1 joule. Both are correct though, and so you choose the one that you want to use. Let's get some practice converting energy. In the first one, you're asked to convert 45.3 joules to calories. The second one, you're asked to convert 3.483 calories to joules. Pause the video and use your conversions that you just learned to help you out. Then resume the video to reveal the answer. All right, we're going to set this up with dimensional analysis. Always start out with what you're given, 45.3 joules. Now, if you use the first conversion, you would have 4.184 joules on the bottom for every 1 calorie. However, if you use the second conversion, you would have set it up like this, 45.3 joules, and you know that for every 1 joule, there's 0.239 calories. No matter what you do, you'll still get the same answer. The answer is approximately 10.8 calories. The second one should be approximately 14.57 joules. This concludes the video lesson on energy units and measurement. The next video lesson is all about specific heat.